Okay, so I'm re-recording this video because I made an error the last time that I want to address. But what we have here, so a pole set up to support a platform. Platform has a mass of 1,000 kilograms, 1 metric ton, and the wind causes a horizontal force of 100 newtons to be applied. And then we want to basically figure out if the pole is 2 meters long, what diameter does the pole need to be, if it's solid, in order for the maximum von Mises equivalent stress to not exceed 200 megapascals. So since we're worried about von Mises, that's an indication this is a ductile material. So if we're saying that we don't want it to exceed 200 megapascals, then we're saying that maybe it's maybe we're aiming for a safety factor of 2 because this particular material has a yield strength of 400 megapascals, or whatever it happens to be. But we have a chart here, a diagram, and I'm going to outline the coordinate system I chose this time around, and I'll discuss that. So here I'm going to make the x direction, the positive x direction, vertical upwards. I'm going to make the y direction to the left there, and then the z direction will be coming out of the page. But that load is, there's 2 loads, and each of them are going to cause a stress of some sort. Now, we're going to be worried about the bending, and we're going to be worried about the axial. So the axial will be caused by the weight pushing downwards. The bending will be caused by this 100 Newton wind force here. Now there's also going to be some transverse shear arising due to the direct shear load of the 100 newtons. That having been said, the location where that occurs is not, at the point where we're worried about the bending stress being the highest. That is a location where the transverse shear is 0, because if we have the direct, we've got some sort of bending moment. The bending moment's about this axis due to a shear load. At this point, and at this point at the top and the bottom here, those are where our bending moments, those are where the stresses due to our bending moment is the highest. And at those points, our Q is equal to 0, because the area separated from the neutral axis but from that point is 0 as well. So shear is 0 at those points as well, the transverse shear. So we're only, in this instance, we're only worried about the axial and the bending. So for the axial, the force, stress is given by the force divided by the area. So in this instance, we're given the mass. It didn't say where it is, but let's assume it's somewhere on Earth. So our G can be approximated as 9.81 meters per second squared, and the mass is 1,000 kilograms. So therefore, the force that will be induced by that weight will be 9,810 newtons. So that divided by pi over r squared. In terms of r squared, that ends up being a negative 3,129 newtons per r squared. So again, that'll be negative because it's compressive. For the bending moment, so this is where I'd initially, I got the calculation right for what the magnitude of what the moment was. I got the in my initial video. I also had ended up picking the right location. Problem was is that there was a negative sign that didn't cancel out, and I kind of just assumed it was. So the issue here is that basically the initial coordinate system that I had chosen was something that looked like, I'm just going to draw, so I had this in the y direction, I had this in the, this in the x, and this in the z. So I believe, and basically what ended up happening is when you plugged in the proper values for the moment about the x-axis and the y value, it ended up giving the negatives didn't cancel out properly. Now I believe the problem there is if you stretch back to recalling the how cross products work way back um, to basically kind of the start of your statics class. Kind of when you have, like, say, an x vector crossed with a y vector, that could be positive. But if you have the same y vector crossed with the x vector, say positive, that'll be negative. When you switch the orientation, sorry, the order in which you're doing your crosses, it switches the sign there too. So the problem is that the formula that was being used for the bending, the sigma bending is equal to negative my divided by I. That was based upon a beam that has some sort of bending moment about the z-axis when the x-axis is along the length of the beam. Sorry, no, the x-axis is along the length of the beam, the y-axis is in the vertical, and then the z is kind of coming out of the page like that. So the initial the coordinate system that I chose here, basically it didn't match the coordinate system that this formula here was derived for. So basically what I had to, in order to fix that, what you want to be doing is you want to be choosing a coordinate system that matches the coordinate systems for the formulas you're using. So basically here, this setup that we have up here, that's basically the same as a cantilever beam attached to a wall. Just kind of rotated. So x in this direction, z coming out of the page here, and then y in this direction. So yeah, thank you to the student who pointed that out, or, well, asked the question because it was confusing and allowed me to realize that I had made that mistake. So anyways, long story short, the moment that we have here about the z-axis is going to be a negative moment because it's a clockwise moment about the z-axis, whereas a counterclockwise moment is defined as a positive moment. Positive. So, and the magnitude of that is 1,100 newtons times 2 meters is equal to 200 newton meters. Negative 200 newton meters. Our I there is just a function of r. And then the y. So again, we need to pick the y at the point where the compressive we need to pick the y at the point where the stresses induced are compressive, because the axial force is compressive as well. So basically we're worried about the worst case scenario here. So we need to choose the case where that's causing a compressive stress. So basically on our diagram here, that's going to be occurring at the negative at negative r. So it's going to be occurring right here at that corner there, which based upon the coordinate system we chose this time around is negative r. So our beam bending formula, negative times the negative moment. When the moment is negative, these two cancel out. Time, so 200 Newton meters times negative r divided by pi over 4 r to the third. So, sorry, r to the fourth. And then we can cancel out one of those r's, giving us r to the third. Move the 4 up to here to give us 800 Newton meters. That was, sorry, to give us negative 800 Newton meters divided by pi r to the third. 800 divided by pi is 255-ish. And what I'm also going to do here is I'm going to convert the meters to millimeters by multiplying by 1,000. So it'll be negative 255 times 10 to the 3 Newton millimeters per r cubed. So both of those stresses are acting in the, oh, actually, I forgot to change that. They're acting in the x direction. Normal stresses, no shear. And as a result, we can just add them together. So the maximum stress that we were told needs to be 200 megapascals. So that 200 we're expecting yielding at 200 megapascals. So that's the maximum absolute value of the stress that we can withstand before this thing starts to yield. So just absolute value of those two things added together, and then plug it into Wolfram alpha and solve for r min is equal to 11.33 millimeters. And we just, as per usual, we can do a quick calculator check to ensure that our Wolfram, that we plugged in the right values into whatever thing we're using to solve for. So 3123 divided by 11.33 squared plus 255,000 divided by 11.33 cubed, and that gives us, that's reversed, isn't it? That gives us 199.6. So looks like we threw the values in there, right? So that is that, and sorry for making that mistake again. Do your let me think here. You need to develop an intuitive understanding of what what sort of loads cause compressive and tensile stresses where, and B, use the coordinate systems that match what the equations were developed for. So if you end up getting some sort of mismatch due to a wonky coordinate system or what have you, you need to be able to tell when that happens by having an intuitive understanding of what's causing stresses where, and that'll just come with time. So yeah, thanks.